Okay, this video is going to be for explaining relative velocity and how we can calculate it. And that's going to be in two parts. So first I'm going to explain the derivation of relative velocity equations again, and then in the second part I will work through the burrito relative velocity example that we did in class, okay? So to think about the relative velocity between two different frames, we're going to first draw our two example coordinate frames. So our first coordinate frame we're going to call A, and then this is our x-axis in frame A, and this is our y-axis in frame A, okay? And then we're going to consider some second coordinate frame B that's got these axes here, xb and yb, and the coordinate frame, the reference frame B, might be moving relative to reference frame A, but we're going to draw it for just a moment in time. So at this particular moment in time, this is what they look like. And we're going to consider some object, which I'm going to draw this time because I think some folks were confused before about where our object was. So we've got this object here, some orange blob, and its position in frame A we can draw here by this vector that we'll call R from the origin in reference frame A. Okay, so this is a vector that points from the origin in frame A to our object. So it's to the object in frame A, relative to frame A. Okay. Now, I'm going to draw, make it be a different color. So now we can also draw a vector in reference frame B that goes from, oops, go away. Oh, I can't get that to go away. Oh, there it goes. From the origin in frame B to our object. Okay, so we're going to call that R to the object in frame B. Okay, and so in reference frame A, this gray vector here shows the position of our object, and in frame B, this purple vector here shows the position of our object. And we'd also like to relate those to each other, and so to do that we need to draw, a different vector that goes from the origin of frame A to the origin in frame B. And so we're going to call that R BA. So this subscript means that this is the position vector of frame B in frame A. So our first one, our first subscript is the object, and our second subscript is the frame in which that vector is written, right? So same thing in each of these. So this is the object in frame A here, this is the object in frame B here, and this is frame B in frame A. Okay, so that's the way that's the convention on those subscripts. All right. So from just looking at these vectors, right, we can see that R, let me use my same colors. R of the object in frame A, that vector, is the sum of those other two vectors, right? It's R BA plus R OB, right? You should be able to see that from looking at the geometry, right? If we consider going from the origin at A and ending up at the object, we can take either path to get to that object. So those two vectors sum to the same, okay? And if we wanted to write this in terms to get R of the object in frame B by itself, we could also write this as, and I'm going to just switch to gray again so I don't keep switching colors all the time. R OB is R OA minus R BA. Okay. And let me add one more thing, which is that all of these might be a function of time, right? So the object might be moving, And if the object's moving, then the position vectors in each reference frame are going to change. And then the two reference frames might be moving relative to each other, in which case RBA will also be a function of time. All right, now we want to consider the velocity in our two frames. So velocity in frame A is just the time derivative of our position vector, right? Which is a function of t. That's just, we can call that the velocity of the object in frame A. And then we're going to assume our A frame is kind of our default reference frame, and then we want to think about how to calculate the velocity in frame B relative to that one in frame A. So velocity in frame B is going to be ddt of the position vector of the object in frame B as a function of time. And then I'm going to plug in this expression for the object in frame B position. So that's the time derivative of the position of the object in frame A minus the time derivative of the vector that goes to B in frame A, to the origin of B in frame A. So this first term is just the velocity of the object in frame A that we already calculated. And then the second term is the velocity of the B reference frame in the A reference frame. Okay. And these both might be functions of time too. So velocity itself could be changing. Okay. So notice that to find the velocity of the object in frame B, if we know its velocity in frame A, we only need to know the velocity in that second frame. We actually don't need to know the position of the origin at that particular moment in time. Okay, so for example, we could have, if we go back to our cartoon or our diagram, B could be moving, okay, to the right, say. So say this whole frame is moving to the right relative to frame A. In that case, the velocity of that object, if you're sitting in reference frame A, so we've got a little person hanging out in reference frame B, so say that's a car, for example. Now, I'm drawing this car that's in reference frame B. If they're moving to the right at some velocity, VA, this is the velocity that coordinate system is moving in frame A. The apparent velocity, or the velocity in that frame of this object, is going to be whatever its velocity is in frame A minus this speed here of the frame itself, right? In other words, it's going to look like it's going backwards relative to what it looks like in frame A because this person is moving to the right, okay? All right, and then in the next video, we will concretize this by applying it to our drone example.